Hi guys. Super sorry that this is not like Discord recorded. We recorded it, but then the stupid we freaking use Craigbot and this shit records. Oh, I swore. Sorry. This only records the freaking audio. So I'm just gonna go over a really quick recording overview of today's just because some people asked for it. And so today we did min stack and evaluate reverse polish notation. It's part of our stack series, and yeah. So really quick intro into stacks. You can think of a stack kind of like a bookcase almost. Um, and so imagine if we had no, where'd it go? Oh, here. If we had a bookcase, but multiple, right? A stack is kind of um, it's kind of it could be represented by a bookcase, right? So if we wanted to add to the stack, you have to put it on top. And if you wanted to get something out of the stack, the only accessible one is from the top. And so um, the way you can think of a stack this way is you can only add to the top and you can only take from the top. And so if we were to represent this in a data structure, right? What if we just rotate this and do the same thing? Then it would still be like taking from the top and then adding and taking from the top, and then if you add it to the top. And so this is very easily represented by just an array like so. And so the way you can think about it is if we want to add to the array, we can just append. And if we want to see the very last value, well, we can just access the -1 index. And so that's kind of the concept of a stack. And so moving forward into min stack, the problem for today. The problem, if you could you could pause and just read it, but I'll just get into it. A min stack is basically an implementation of the stack algorithm and stack data structure, except there's an extra function called get min. And now get min, what that does is that imagine we had a stack of a bunch of random sized books. How can we constantly always get the smallest book in O of 1 runtime? And that's the trick there. Oh no, oh wrong problem. Sorry. O of 1 runtime, and that's the trick there because uh, like we would think it's easy to implement the get min, but that would mean that we the easiest brute force way would be to iterate through and keep comparing and finding the minimum value, but that would take a end time, and we want it to be constant. And so that is just the kind of the problem that we're trying to tackle right now. You can pause and take a couple of moments to try and code it up. And if not, then I'll move on to the solution. So the best way to think about this is to first try and implement it like a stack. And so there are three main functions that work like a stack. And so this could be represented, like we said, a stack can be represented by an array, right? Because it's just a book stack or bookcase that's rotated to the side. And so this is a good format and data structure that we can use. So first we can think of it as something like a stack equal to an array. And so that could be going in the, oh, sorry, I totally forgot the init function. Initializing and declaring a stack, which is an array. And so, like I said, right, the push functionality would be appending, so that would be an append. The pop is removing the final element. And so luckily for arrays and list in Python, there is a dot pop. Top would mean getting the very last element in the array. And so this could look like accessing this, the last element. And so that would be a good representation of the stack. Now, how exactly would we do a min stack? To be able to oh, I keep clicking the wrong person. Problem, sorry. To be able to get the minimum element in the stack, one possible way or one possible solution of thinking is to bring in another stack to keep track of the minimum value. And the reason we know we can bring up another stack is because we want constant time. And what better way to do constant time than by just accessing the very last variable? And so it would be nice if the very last variable was always the minimum value. And if that's the case, then we know that we can just get from the top or access the -1, and that would give us the minimum value. And so that's the idea we're going for. So obviously conceptually, right? The goal to get constant time is that if I were to initialize this as another stack, the ultimate goal is so that we can do this in minimum runtime. And so this means that these are pretty set. This sounds pretty good. And so how can we implement that, right? How would it look like if I added a book? And so that's a great question that we can just try and replicate. So let us pretend these books are equal to a certain amount of numbers. So the big book is size 3, the small book or medium size is 2, then it's 3. The small book is represented by 1, and then this top book is represented by 3. And so obviously, if we understand it correctly, get min would be getting 1 at the very top, and then 2, and 3. Okay, so let's run through a situation where we are pushing to the regular stack. So if I were to push this one, right, then obviously it's going to be a 3. And since this, and so that's just a regular stack, sorry. And now how about our minimum stack, right? We're trying to keep track of the minimum value that we have been seeing in the stack. And so since the stack is empty, right, we know that we can just, there is no minimum. And so whatever value that we put here is definitely going to be the minimum. And so obviously we're just going to put 3 and transcribe it over. Now moving on, we're going to input the next book, which happens to be smaller by coincidence, which is a 2. So just in a regular stack, it naturally just adds. And so now when we're looking at this, interesting. How would we do this? So obviously we're keeping track, using the stack to keep track of the minimum value that we've been always seeing. Then naturally, it would make sense to compare our current value and the value that we're finding in the stack, or the minimum stack. And so we're going to have some sort of comparison, right? Like to see that 2 is smaller than 3, or find the minimum between these two. And so that's a good hint because min is in the name. And so obviously there's some minimum call to the minimum function. And so naturally it would look like a 2 here because we're keeping track of the minimum value in the stack. Hopefully that makes sense. Moving forward, oh, sorry, no, hey, chill. Moving forward, we're going to paste in another book, and that's a size 3. And so we see like the minimum between 2 and 3 is obviously 2. And so currently at this current index, right, in this current stack, the smallest value is 2. And so we should just keep track of that, right? Like at this current input of this book, the minimum is still going to be 2. And so that's what we're keeping track of in this array. We're just keeping track of the minimum value at each index. So hopefully that makes sense. I'll just finish through the problem. So now we have a book of 1, and so this is a 1, right? And after inputting that in, we're going to compare the two values. We're going to compare our current value and the current minimum value in the whole entire stack. And we see that, of course, 1 is smaller than 2. And so now we're updating that with 1. Lastly, we're going to put the 3 book in, and this is a size of 3. And so naturally, we're just comparing it, and we see that these are, we see that the min between these two numbers is still the 1. And so we're going to keep track of the 1, because in this current stack right here, a stack of 5 and the index of basically 5, we see that the minimum value is still this 1 book. And so that's what we're keeping track of. And it's great, right? Because like in the, this is a great representation because if we're looking back and we're trying to accomplish this goal right here, we just want to access the last value and see the minimum value. And so is this true? In this current stack, if we access the last value, yes, it is indeed 1. And so that's great. And so that's some logic that we have to do when we're implementing when pushing. Lastly, talking about the pop, if we were to go backwards and remove it, let us take, for example, this case right here. So if, let's say we're trying to, if we're trying to pop this, right? That's a good example. So we're trying to pop this book, and so naturally, if we pop it, it just removes, right? And so this would remove. And obviously, like now this is kind of like uneven, but we don't really know what to do with this minimum stack right now. But let's just say we move on, right? If we were to pop again from, if we were left with these 3 books and we wanted to find the minimum value, we would call this function, and this function would just view the last item in our minimum stack. And we see that we still are stuck on the 1 because we are still thinking that this book is here. And so when we're popping, we should make sure to pop both of them so that everything is updated with the index because this minimum stack represents the minimum value at this current index. So if the index is 3, which means there's 3 books, the minimum value at this index is 2. To reiterate, it was like this. The minimum value would be 2 still, right? If it was here, right, at index 0 or index 0 basically, where there's only 1 book, the minimum value shouldn't be 2, right? If I call get min, I shouldn't get 2. And so naturally, right, the void pop would pop both functions or both stacks. And so when looking at this code moving forward, we can see that this is pretty much the implementation. We have 2 stacks, the stack of the regular one and the stack of the minimum. And then we can do the easier functions first, right? So like I said, when we pop, we're going to have to pop both. The top is just returning the top of the regular stack, which is intuitive right here. The get min is just returning the top of the minimum stack, which is intuitive right here. And the funky code right here is the push. So naturally, right, we're obviously just going to append if it's to the regular stack whenever we see a new value. But the trick now is having to figure out what kind of value to append to the minimum stack. And so the base case is, remember, if we have Wait, is it possible? Oh, sweet. If we have this, right, and we just added the 3 to the book or to the stack, well, there's no other minimum yet because it's the only value. And so if the minimum stack was empty, naturally we're just going to put 3 even though it's such a big number. And so that's the same as actual logic here. If the minimum stack is empty, we're going to append 3 or the value. Else, right? Else we are going to do the logic of comparing what happens when we add a 2. So if I add a 2 book, yeet, here we go. If I add a 2 book here, then we see that, oh, hey, wait, 2 is smaller than 3. So we're going to compare and pick them in and then put them in here. And so that's exactly what's happening, right? I'm going to get the current value. I'm going to get the minimum value in our stack or the very top value, compare them, which is by doing min, and then append that comparison here. And you see if I run this and submit it, if it doesn't work, I might cry. Let's go. Okay, it's super slow. I swear it was faster. No, 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 no. I swear it was faster. Yeah, yeah. See, 72%. Same code, I think. I don't know. But yeah, pretty cool. Awesome. Gnarly. Yeah, so that would be constant. The runtime would be here. Appending is everything is just constant runtime. Just because we don't have to iterate through the whole entire list and we can just access from the top. So yeah, that's min stack. You can pause to kick that all in. But now in our accelerated video, we're going to move forward to evaluate reverse polish notation. And so in this problem, you can take a pause, or you can take a moment and pause and read this too. But I'll go into like basically understand or explaining the conceptual understanding of this. And so we're given an array of strings and tokens like this. And basically, we're going to want to be able to parse it and then return the computation at the end. And how this technically works is as follows. So numbers will just be represented by numbers, right? But whenever we reach a notation that is an operator, which is plus, subtract, multiply, or divide, we're going to be executing that operation on these specifically the past two parameters. So if we see 2, 1 plus, that means we're specifically adding 2 plus 1. Likewise, if we specifically adding 2 plus 1, and then when we see the 3 and the multiply, we're going to be accessing multiply on the 3 and then whatever output we got from 2 plus 1. And so if we run through a quick example, right, for conceptual understanding, hopefully, yeah, if we run through conceptual understanding of how this exactly works, right, we're going to see that, okay, when we're parsing through or for loop, imagine we're for looping through this list. So if we're currently at 2, okay, well, we're going to remember that we have a 2. And then when we move to the next value, the 1, we're going to remember that we have a 1, right? And then when we move to the plus, oh, hey, well, by the rules of just purely by the rules of what like reverse polish notation is, that basically means we are applying the plus to the last two elements, and that would be 3. And so now we're storing the value 3 in our heads. So now when I move on to the next index, we're going to have a 3. So since it's just a number, we're going to remember that number. And then when we finally reach the multiply, it's going to be, hey, okay, the multiply on this. And so that would give us 9, and then we would return 9. And so naturally, if you're thinking about this, you can technically see how, well, we kind of need a stack, right? Like, if you think about it, we're kind of just keeping track of the last element. And so if I were to repeat the same exact process but with a stack, we can see that, okay, if it's just a number, starting over back here, if it's just a number, then we're going to add it to the stack, right? We're just going to remember it, quote unquote. Likewise for the 1, so I'm just going to move it to the plus already, but right here. But then when I reach the plus, right, that's an operator. And so if we see an operator, we're going to want to apply the operator to the last 2 elements in our array. And so how can we access the last 2 elements in our array? Well, technically, these aren't here. So accessing the last 2 elements would be popping twice. So pop once. I think you guys get the point. It's so ugly. Pop twice. Sorry. So you can pop twice. And then that would give us the last 2 elements. And then we apply the operator to it. So that would be a 3. Right? So perfect. So now, after that, we're going to add it back to the stack, right? Because that's now what the number we're remembering. So we're remembering a 3. And so now this is all void. And so now in our stack, we only have a 3. Then moving forward to this, during this array, we're going to reach another 3. So obviously, we're just going to append that over. And then lastly, we're going to reach up the multiply. And so multiplying is going to fetch the last 2 elements, which is these, and then multiply them together. And then that would give us a 9. 9 right here. And this is the very last value, right? The first index value is going to be the very last value at the very end. So that's the perfect conceptual understanding. If you want a bigger code piece, you can conceptually understand it here by seeing that when we go through to 10, right? 10 is a number, so we're going to add 10. 6 is a number, so we're going to add 6. 9 is a number, blah, blah, blah. 3, and then we reach an operation. So operation would take the last two numbers that we remembered, and we see how we're taking like the last ones we remembered, right? So that's very similar to taking the last one we put in, which is going to be the top of the stack. Or essentially, we're just going to take in the pop of the stack. And so we're going to take those two, add them together, and we see, oh, no, sorry. Hey, that's not actually a number. It's 12. Perfect. So now our pointer is going to move on to the 11. And then, good to know, okay, 11's here. And then we can move on to the multiply, and then we're going to multiply these two together, right? So that's negative 132. And then we're moving to the divide. And just a quick note for divide, the way divide works is, or it's always going to be like the second last number, and the first last number, like in terms of like in terms of the operations, it's going to be like second last number. I don't know. Okay, it's second last number, so 6, and then divided by the first last number. So it's kind of like in consecutive order. And there's one quick caveat, got me stuck for a while. Just be sure to read through all this, but basically the division is always going to truncate towards 0. And so basically what this means is we're just going to have to cast this in later to like basically floor divide it. So yes, that is conceptual understanding. And if we were to just basically look back into code, right, it's pretty simple. So my code is probably not that efficient, but I just like keeping track of all the operators. And I also did this, so this is actually an solution, but we're gonna have to keep track of all the operators, and then just a stack like usual, right? And then that's when we're gonna start iterating through whatever our list is. And so I just call each individual token a token, and this is the logic. But for now, we can just think that we remember that we know we ended off with a value that is within the stack or the first element, and so we're returning the first element of the stack. So that's pretty helpful. And then now we can look through the logic. So obviously, right, if the token is in the operator, then we're going to want the past two elements because we know we have to apply the token or the operator to the past two elements. And so this is purely just getting the past two elements. I cast them as an int because these are strings. And then simply this is just filling out like hard coding just all the specific operations. So plus, multiply, subtract, divide, yada yada. So those are the cases. And then the if case, if it's not a token or operator, would be to just that it's just the token itself or it's just a number. And then at the very end of the for loop, we're going to append the value. So this would mean we're either appending the number here or the computation of sorry. Oh no, 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 no. How dare you? We are either returning a value of 9, right, for example, or we're either returning like the value of the computation from the plus. So that would mean 9 plus 3, which is 12. And so either way, we're appending a value, but that value is set to either the computation or the value of the number itself. And so yeah, that is a solution you can run and see that it is pretty fast. And this should be O of n time because we only iterate through the list once, which is amazing, cool, and fun. So yeah, that is a quick accelerated summary of what we went over in the Discord today.